Good morning, everyone. I thought that today I would redo the chapter 2 review so there's no background noise or bells or people, interrupting questions and things like that. So I'm going to do this in its entirety, and I hope that this helps you. Okay, so the first question is, suppose f of x equals to root x. We want to calculate the average rate of change between 9 and 9.1, the average rate of change between 8.9 and 9.0, and then estimate the instantaneous velocity at x is equal to 9. All right, so let's move this out of the way, and let's do this. So we have f of x equals root x. That's our function, right? And in the first case here, in part A, we want to estimate this between 9 and 9.1. So remember that the average rate of change is equal to f of b minus f of a, what's that, over b minus a. And don't forget that in your interval, this is your a and this is your b. So, it's f of 9.1 minus f of 9 over 9.1 minus 9, right? And the thing is that we're going to have to compute what these two values are. So over to the side, f of 9.1, well, we don't know what that is off the top of our head, so we just leave it like that. And f of 9 means what is the square root of 9? And we know that one, it's 3. So if I take those input and output values or take the output values and substitute them in here, then what we're going to have is root 9.1 minus 3 over 0.1. And then you would use your calculator. And of course, I forgot mine in my bag, so hang on one second. Okay. Ciao, Ella. So, using my calculator, if I compute root 9.1, okay, minus 3, and hit enter, I get this number here, and then, I have to divide that by 0.1. So divide by 0.1, and we get 0.166. So the average rate of change over the interval from 9 to 9.1 is about 0.166. In B, what we're asked to do is to compute the average rate of change over the interval from 8.9 to 9. Okay, so let me make this straight here. Straight. So again, we're going to have the average rate of change is f of 9 minus f of 8.9 over 9 minus 8.9. Well, we know f of 9 from the previous one is 3 minus root 8.9 over 0.1. And again, if we put that into our calculator, we're going to have 3 minus root 8.9, hit the equal key, and then divided by 0.1, we're going to get 0.167. Okay? So for part C, when they ask us to estimate the instantaneous rate of change, what we know to do is we take our two values, the one from the right and the one from the left, add them up and divide by 2. So we would say it's 0.166 plus 0.167 divided by 2. And I want to see something. Yeah, so even if I use these numbers, so normally I wouldn't round until the very end. But anyway, when I enter those numbers exactly, I get 0.1665 or 0.167, which would be the best estimate of instantaneous rate of change that we could get at that point. Right? It's not the best, but it's really good. In number 2, we've got the ball, right? The ball's dropping. So again, a ball is falling from a height of 400 feet toward the earth, and the in time equals seconds, the ball drops a distance of 16 t square feet. So A, how many seconds after release does the ball hit the ground? Right. So again, what we know is that the ball, is 400 feet. I'll put it up here on a stick, 400 feet above the ground, right? So if we drop it, the furthest it can fall is 400 feet, all right? So in part A, what you're going to have is 16 t squared is equal to 400, okay? Because this represents the distance that the ball drops. Okay, and we know that that has to equal the total distance, which is 400 feet. So if we solve this thing, we divide both sides by 16, and we get 25. So the time is 5. Okay, so remember, you're going to get a +5 and a -5, but you can't have a negative time. All right, so you choose positive time. So the ball hits the ground in 5 seconds. That was part A. In part B, we want to find the average velocity of the ball during the fall. What is the average velocity? Well, again, the average velocity is f of b minus f of a over b minus a. Now, the reason why you found the time it took for the ball to hit the ground is because you need an interval of time. And so you started at time 0 before the ball was dropped, and it took 5 seconds for the ball to hit the ground. So your interval here is from 0 to 5. So that's what you're looking for, f of 5 minus f of 0 over 5 minus 0. All right, well, what is f of 5? F of 5 is 16 times 5 squared, which is 400. And f of 0, of course, is 0. So replacing these components in here, we're going to have that the average velocity is equal to 400 minus 0 over 5, and that's 80 feet per second. Okay, because we're talking about average velocity, so we need to make sure we include the units. And the units in the problem are in feet and seconds. In part C, they want us to estimate the instantaneous velocity when the ball hits the ground. So remember, when the ball hits the ground, it's going to keep bouncing, all right, for a little ways. So what you want to do is you want to choose a point really close on the left and really close on the right. And if you need to, make a little number line. This is when the ball hits the ground. Just a split second after, time is 5.1. And just a split second before, it's 4.9. And use those values to estimate your instantaneous velocity. So you could say, it's f of 5.1 minus f of 4.9 over 5.1 minus 4.9. In other words, this is right in the middle, so you're encompassing it within. The other thing you could do, f of 5.1 minus f of 5 over 0.1, and you could do f of 5 minus f of 4.9 over 0.1, and you can compute these two here. And once you get the values for each, just like we did in the first problem, add them up, divide by 2, and get the answer. All right. So, again, I don't know what f of 5.1 is, so I'm going to have to use my calculator. It's 16 times 5.1 squared. And what we get is, 163.2 exactly, minus, now if I do 16 times 4.9 squared, I get 384.16. That's 0.2. So if I go ahead and subtract those, 163.2 minus 384.16, and I divide that by 0.2, hang on a second. I always make an error when I use my calculator. I think I made, let me just double check these numbers here. So 16 times 5.1 quantity squared is definitely, oh, it's not 163. So yeah, I must have not hit a button right or something, or all the way. It's 416.16. And let me just double check the other one to make sure. Because like I said, I don't like this calculator because sometimes you press a button, but you don't press it enough. So this one's correct. And if I subtract that from 416.16, I get 32. So this is 32 over 0.2. And we get 160. All right. And again, we're looking at instantaneous velocity, and so that's in feet per second. So those are the first two. In number 3, I'm going to just use this table here. So again, in number 3, we're given a table, a distance time table. All right. Time is the input, distance is the output. And we want to find the average velocity between 1.3 and 1.9. All right. So again, if you have to, it doesn't matter whether you use a bracket or whatever, it's for your purposes. Think of the interval that you're working in. Okay. And what we know, so I'm going to move this over here. What we know is that the average velocity is equal to f of 1.9 minus f of 1.3 over 1.9 minus 1.3. F of 1.9 is 5.3 from the table, right here. And f of 1.3 is 5.1 from the table again. And 1.9 minus 1.3 is 0.6. And 5.3 minus 5.1 is 0.2 over 0.6. And, this is 1/3. Now, again, in B, he chose the wrong number. So I mentioned this in class. He wanted you to estimate the instantaneous velocity at 1.9, but if you look at his answer, he was actually looking for this one, okay? So if we used the endpoint, the only thing we could do to estimate this is do f of 1.9 minus f of 1.8, okay, over 1.9 minus 1.8. And of course, if I use that, it's going to be 5.3 minus 5.6. I'm going off the edge here, over 0.1. And this is 5.3 minus 5.6 is negative, that's going to be negative 0.2 over 0.1, which is negative 2. Again, that's for the endpoint here. But if you wanted to do, this one here in the middle, or any one other than the endpoints, you would do the same thing. So I'm going to do the 1.5 just to make sure it's understood. And if you get that, then, fast forward the video. But if I wanted to estimate the instantaneous velocity at x is equal to 1.5, for instance, that's my point in question. So I would choose a point to the left. So I would say this is f of 1.6 minus f of 1.4. That's a point to the left. So here's a point to the right, a point to the left, over 1.6 minus 1.4. F of 1.6 is 5.7. F of 1.4 is 5.2. 1.6 minus 1.4 is 0.2. So it looks like we have 0.5 in the numerator, and it looks like we have 0.2 in the denominator. And so anyway, that would be 2.5, right? 5/2, roughly. Sorry, I went off the paper there a little bit. Hi, Ella. I know. I have to make a video for the kids. Got to make a video for the kids.
They have to learn their mathematics. Yes, they does. They have to learn it.
You want to go under the camera? Okay, let me make my video, okay? It's too early to play. Go lay down, go lay down, go lay down. Thank you, Ella. Okay. Get down, I gotta work. Get down, come on. Sorry. She's a very high needs dog, high maintenance. All right, in part 4, we're asked to find the, oh no, I just dropped all my papers. That's okay. In number 4, we're asked if the average rate of change of a function from 1 to 9 is 3, and f of 1 is 5, then find f of 9. And so what I know is that the interval I'm using is from 1 to 9. I know that the average rate of change of this function, or any function, can be given by f of b minus f of a over b minus a, right? So in this case, it's f of 9 minus f of 1 over 9 minus 1. And they're telling us that this average rate of change is 3. And they want us to find f of 9. So, they're also saying that f of 1 is 5. So, no big deal, right? This is an 8. So we have f of 9 minus f of 1 over 8 equals 3. Multiplying both sides by 8, we're going to have f of 9 minus f of 1 equals 24. Now they told us f of 1 is 5, so I can replace that with a 5 and add it to both sides to get f of 9. Okay, and that's all there is to that very cute little problem. In number 5, you're given g of x is equal to x squared plus 5x. And you want to find the average rate of change from, okay, so they're giving you the interval a to a plus h, okay? They didn't even need to say any more, right? Because we know that the average rate of change of any function is f of b minus f of a over b minus a. And you have an a and a b here. This is your a and this is your b. They're just weird looking, okay? They're just not numbers. So you're going to have to compute g of b, g of a plus h, right? Well, that's just a plus h quantity squared plus 5 times a plus h. And if we expand that out, that's going to be a squared plus 2ah plus h squared plus 5a plus 5h. And that's the end of that. We can't clean it up. We've expanded it. We're done. G of a, of course, is simple because we plug an a in for every x, and we get a squared plus 5a. So we're going to take these two and fill in the pieces, right? So a rock is equal to a squared plus 2ah plus h squared plus 5a plus 5h minus, from the formula, g of a, which is a squared plus 5a. Remember, put it in parentheses so that way you don't, do not forget to distribute your sign. Okay, this is my b minus a on the bottom, and you notice the a's are going to cancel, so you end up with an h. So, okay, so here goes the dog at 6:30 in the morning. So, cleaning up the top now, I've got a squared plus 2ah plus h squared plus 5a plus 5h minus a squared minus 5a all over h. And the 5a's cancel and the a squares cancel. I'm gonna move over here into this little square that I'm creating because this is old stuff. So the average rate of change, and I'm going to factor out an h in the numerator, is h times 2a plus h plus 5 all over h. The h's cancel. So our average rate of change is just 2a plus h plus 5. That's the end of that. There's your answer, okay? It's an expression. And in part B, they want you to find g prime of a. Well, this means find the derivative, and the definition of the derivative is the limit as the width of the interval gets really, really small of f of a plus h minus f of a all over h, right? The limit of the difference quotient. Well, we already found this part up here. We already did the hard work. So we'd say g prime of a is equal to the limit as h approaches 0 of 2a plus h plus 5. I can't simplify this expression anymore. So what that means is at this point I'm going to take the limit, meaning I'm going to plug the 0 in for h. So we'd say g prime of a is equal to 2a plus 5. So what we found is the derivative of the given function at a point, okay, and x equals to a. That was number 5. Number 6 was a very simple problem. Some of y'all, I think, made it a little more difficult than it is. But you see, this is what I mean when I say this is a very conceptual section, because you have to apply what you know. So you look at this thing and it says, sketch the line whose slope is this. Well, this is just the slope of some line. You know f of b minus f of a over b minus a, right? You know that the interval is from 1 to 4. Right? This is b minus a downstairs, so it'd go ab in your parentheses or your brackets, right? And so you go to where x equals to 1, you go up to, you touch the graph, and you plot a point. And you do the same thing at 4, and you connect them with a line, a secant line, and you call it L sub 1. And then in B, now they're asking you to sketch a line whose slope is this. Well, this is a slope of a tangent line, right? This is our limit definition of a derivative at the point where x is equal to 3. So you go to where x is equal to 3, you plot a point, and you try to draw the best tangent line you can through it and call it L sub 2. And that was all there was to that problem. Number 7, another ball problem. I want this paper, and let me get more paper. Because I always need lots of paper. Okay, so here we've got a ball thrown up in the air with the given velocity of 96 feet per second from a height of 112 feet. And the height of the ball is given by this function here. And so remember, I did this without a calculator. And you should be able to also, because remember, this is no calculus needed. This is algebra 2. In fact, you haven't done, oh, look at that thing just flying like that. See the waviness? Like a river. Maybe if I put this here, it'll calm it down. I think it's because I'm so close. So anyway, back to the ball problem here. So let me write this function down here. So we've got h of t is equal to negative 16t squared plus 96t plus 112. Remember, this is the height of the ball initially, right, before it's dropped. So if we want to find the maximum height that the ball attains, remember from algebra 2, you could find, this is a parabola that opens down because it's a quadratic function. It's going to frown, right? It's going to have a maximum up here. And to find the maximum or the x-coordinate of the maximum, we can use this cutesy little formula x equals negative b over 2a, right? Where in any quadratic formula, the coefficient of the leading term is a, the coefficient of the linear term is b, and then the constant, of course, we call c. So we computed x is equal to negative 96 over 2 times negative 16, right? And I forgot what that was. I think it's 3. Yeah, it's 3. So the x-coordinate of this maximum is 3. And to find the y-coordinate of the maximum, we have to evaluate h of 3, right? So that's negative 16 times 3 squared plus 96 times 3 plus 112. Which turns out to be 256. All right, so it's always the y value that is the height of the function, when x is equal to something, okay? In this case, our x is equal to 3, and the height of the function is 256 at that point. So the maximum height the ball attains is 256 feet, right? That was A. In B, it says to find the average velocity of the ball between 0 and 7. Piece of cake by now, right? We know that the average velocity is f of b minus f of a over b minus a, which is f of 7 minus f of 0 over 7 minus 0. And so f of 7 means I need to plug a 7 in here into this function. So we have negative 16 times 7 squared, which is 49, plus 96 times 7 plus 112. And I'm just throwing that into my calculator, and we get a 0, okay, for f of 7. And f of 0 is nice because if we plug a 0 in here, anything with a t goes away and we're left with our initial height, which is 112. So our average velocity is 0 minus 112 over 7. And if I divide 112 by 7, I get negative 16 feet per second. I'm sorry that I'm doing this with the paper, but I'm doing this on YouTube Live. And everything's backwards on my screen. So when I move to the right, it moves to the left. Oh my God, is my microphone not working? Are you kidding me? Come on. What am I using? What microphone? My Yeti's not working. It's not plugged in. Oh my God.